Hello everyone. You made it to the third video. Very exciting stuff. I know you had to stay tuned, right? You couldn't wait to see, you had to know what was coming for these more complicated equations. I'm so excited. There's more than one step in all of these problems. Yay! All right, are you excited yet? No? All right. Well, we will get to more complicated equations than this, but this is just kind of the intro and saying, hey, you know in the last section how every problem took one step? What if there was more than one step? Does it matter what order you do the steps in? Does it not? That kind of thing. So at the top of the page, we have these steps, or this, if you have an equation and you're not sure how to solve it, these are good steps to follow. Always try this first, and then always try this and this. But I kind of want to develop these steps as we do these examples. So I'm not going to refer to these steps, but if you get stuck in your homework or something and you just want to know, all right, what do I do first? Or what's the next step? You can always come back to these. But I'm not going to really refer to them very much in this section until we're done with all the problems. And then we'll kind of reason out why we came up with these steps and why is that a good order to complete these problems in. Okay, might as well start with the first one. So I guess like in the last section, what you want to do when you solve an equation is to isolate the variable so it's all by itself. So in this first example, I see x is the variable. So in the very end, I want to see x equals something. But notice in this example, unlike the ones in the last section, you have two things that are standing in your way from x being by itself. The 7 that's adding in the front, and then at the same time, the 5 that's the coefficient. So the question is, does it matter what order I get rid of them in? Can I get rid of the 5 and then the 7, or the 7 then the 5? The short answer is there is a right way and a wrong way. I'm going to talk about the wrong way first, just to show why it's wrong. So let's say I thought, I'm going to try to get rid of the 5 first. Why not? So I look at the 5 and I say, all right, 5 is doing what's the operation between 5 and x? Okay, it's multiplication because they're just next to each other. So what I'd want to do is divide by 5. But the thing is, if you divide by 5, you'd have to divide the entire left side and the entire right side, which is not pretty because you didn't really simplify the left side. What you can do, this is a property that we'll see actually probably soon in this class, that the left side, that can be reduced down to the 7 dividing by the 5, and then your 5x divided by 5. Which I don't think you really, it did simplify this thing, because that's just going to be an x. But you created a bunch of fractions that weren't really necessary. So I think the lesson here is, if you have a choice, you have something multiplying or dividing by x, and you have something adding and subtracting with x. You want to first get rid of what's adding or subtracting, and then get rid of what's multiplying and dividing. So that's a big thing to take away from this problem. So yeah, get rid of what is adding or subtracting before what is multiplying and dividing. And you will see that reflected in the steps above, the ones that just kind of give you a general outline on how to solve these. So you notice, I think step 4 here it says, that's how you want to get rid of what's adding or subtracting. And then step 5 is then you want to get rid of what's multiplying and dividing. And don't really worry right now, for the first 3 steps are just for really complicated problems. Most problems, like the example we're working on here, you won't need step 1, 2, or 3. But okay, so now that we've decided it's best to get rid of what's adding or subtracting, I want to get rid of the 7 first here. Since 7 is adding, I guess I think, what's the opposite of that? I want to subtract. Or another way to think of it is, what can I add or subtract to 7 to get rid of 7? Well, 7 plus negative 7 would be 0. That's what I want. So introduce a negative 7 or subtract 7, whichever way you want to think of it. Because that would produce a 0 there. So the 7 plus negative 7, and then the 5x. On the right side, you have negative 22, and negative 7 is negative 29. There we go. Because remember, if you're subtracting, taking a negative and subtracting something, you can think of that as the negative plus a negative 7, kind of. It's kind of easier to think of it like that rather than negative 22 minus 7. For me, anyway. All right, and then the 0 that's in the front, that's kind of silly. I just wrote it just to make sure in my mind that I actually got rid of that 7. So I have 5x equals negative 29, and then I think now there's only one thing left to do. The only thing standing in my way of having x by itself is the 5. And since 5 is multiplying by x, I'm going to want to divide by 5. That'll get rid of it. And at first I kind of panic. I think, uh-oh, that right side is not going to go in evenly, you know? Negative 29 is not divisible by 5. You know what? That's actually awesome. That means I can just leave it like that. Yay! Less thinking from me. Okay, that's not a good attitude to have, huh? I'm sorry. Oh well. But all right, now I think we're good. We're getting somewhere. Maybe we'll try example 2 over here. Probably should have left more room. Sorry, guys. What do we have? We have 2 things standing in the way of our variable z being by itself. The 9's in the way for sure, but the 12/5, that fraction's in the way as well. But like we pointed out in the last example, you want to get rid of what's adding or subtracting with z, the 9, before you get rid of what's multiplying or dividing, the 12/5. So I definitely want to get rid of the 9 first. And since 9 is positive and it's adding with z, I'm going to do the opposite and subtract it from both sides here. And that'll get rid of that guy. All right, so we got on the left side, 3 subtract 9, that would be negative 6. On the right side, just the 9 and the 9 that was there, subtract the 9 would make 0. You shouldn't feel like you have to show that step if you don't want. Just if this is kind of new to you, then it's good to show that, just to remind yourself why it disappears. But you don't have to. All right, now we're just left with, yeah, it's probably just better to forget about it, huh? Once you get the hang of it. All right. Now we're left with a variable multiplied by a fraction. So if you remember in the last section, we did this one way where we divided by the fraction on both sides. But then in the next example, we kind of wised up and we said, you know what? What you end up doing is you just multiply by the reciprocal on both sides. So I'm just going to cut out the middleman like we did in that example and multiply both sides by the reciprocal of 12/5, which is 5/12. That's going to make this process go a lot faster. So it's kind of up to you if you want to try to memorize that, because it's going to save you a lot of time instead of dividing both sides by the fraction. That would always work, but it's just going to take a lot longer. That's the only bad thing. Okay, let's section this off here. So now, where are we? On the left side, I have 5/12 multiplied by negative 6. I can't really have those interact until I put the 6 over 1. And now I can go ahead, if I want to, multiply across, or I can reduce. Because I notice the 6 goes into 12 twice. So let's see, on the left side, what would be left over? 5 times 1 is 5. In the denominator, you have 2 times 1, which is 2. But don't forget, it was a positive fraction a positive fraction multiplied by a negative number, which is a negative. So that answer is going to be negative 5/2 over there. And just to point out, I notice, and it looks like I put the negative on the 5. But actually on a fraction, you have the freedom. If you have a negative on a fraction, you can put it in the numerator. You're free to put it on the very side of the fraction, or you can put it in the denominator. So a negative is pretty free in a fraction. It can go numerator, denominator, side. Just don't put it in 2 places at once. You only have one negative. It can only go in one place. So just in case you were curious, how about this right side here? This is one of those times, like in the last section we said, notice the 12s cancel, the 5s cancel. That ends up just being a 1 times z, which is just z. So all right, the answer must be negative 5/2, or if you'd rather write it, negative 5 over 2, 5 over negative 2. I think mostly like in the homework and if you check your answer in the back of the book when you're studying, you usually see the negative off to the side. They don't really commit by putting it in the numerator or the denominator. So this is probably the preferred one. But just know that all 3 of these they really mean the same thing. It's just the negative to the side looks better. That's all. All right. We're doing well here. I like this. Having a good time. Starting off well. Let's try example 3. Hopefully everything's good. You're having a good time. Not too bored. It's example 3. I notice it looks simpler so far. I'm noticing first that the 15 is in the way of the variable r being by itself. And since it's positive 15, I think what I'll do to get rid of it is subtract 15. Because that way the 15 that's already there and the 15 I'm subtracting will make 0. That's 0. But then notice that the negative doesn't go away. That's in front of the r. So keep in mind, I guess, whatever sign is in the front or to the left of a variable, it sticks with it. So let's see. I still have a negative r. Oh wait, why did I put 11? What the heck? I'm losing it. Is 11 minus 15 11? No. Come on. Come on. 11 minus 15 is negative 4. What kind of rookie mistake is that? Am I right? All right, so we have negative r equals negative 4. And I think we saw this in the last section. We just kind of said it's a good thing to remember that if you have a negative in front of your variable, the best way to get rid of it is divide by negative 1. You know what that does? You probably noticed this already, but essentially that just changes the sign of both sides. Because the left side was a negative r, now it's a positive r. The right side was a negative 4, now it's a positive 4. It's kind of a good thing to remember, just so it doesn't come as a surprise. If you want to get rid of a negative, just change the signs of both sides. All right, looks like 4. All right, looking good. And you're noticing these examples, they're getting more and more complicated. So they're more and more difficult to check your answer for. But I think the more difficult the example, probably the more important it is to check your answer. At least, like I said before, on exams. If you're taking an exam or you're doing a quiz, you probably want to check your answer. But all right, let's try the next one. This one, okay, this is probably one where I'm looking at it and I think, all right, example 4, I see 2/3 plus 1/4 t. I'm not really excited about that. I mean, one fraction's bad enough, like in example 2. But then I have 2 fractions. Hello. This is probably where I would go. Think about the thing that they mentioned in this first step here, up here in the top where the step-by-step procedure is. They say, you know what, if you have, I mean, it says many fractions, but to me, many just means more than one. If you have one, I don't think it's a big deal. But if you have more than one, I don't want to be bothered with a bunch of fractions. Jeez, no one likes those guys. You can, solve it the old-fashioned way. Like if I'm thinking, all right, I want to get rid of the 2/3, I'll probably subtract it to the other side. And then I'll get rid of the 1/4, and I'm just not really excited to subtract 2/3 from 2. I gotta get a common denominator, and that doesn't sound very fun. So there's a little trick that I love. This is my favorite trick of solving equations. It's like it says here, in step 1 up here. If there are many fractions, you can get rid of all denominators by multiplying both sides of the equation by the least common denominator. Because I guess, like we said, as long as you do the same thing to both sides of an equation, then it's a valid move to make. And this one always works. This will clear all your denominators. So what I have to do is think about, looking at the 2 fractions I have within this, what is the LCD between the denominator of 3 and the denominator of 4? I think it's going to be 12, right? The common denominator. So what they're saying is, you're not really trying to get a common denominator. I'm not trying to see both those fractions have the same denominator. What I'm doing is using the least common denominator as a tool so that I don't see any fractions anymore. I know that sounds weird, but I think when we do this process, it'll make a lot more sense. So, as it says, I'm taking the LCD 12, and I'm multiplying both sides of the equation by it. So, I'm going to give it to the left side and to the right side. The left side was 2/3 plus 1/4 t. And I want to multiply it by the right side as well, the 2. So notice though on the left side, you're going to have to distribute this 12 onto both terms. The 12 times the 2/3, the 12 times the 1/4. So I might write that out real quick here. That's 12 times 2/3. Okay, gotcha. But then I have 12 times the 1/4 t that was sitting there. Because again, you have to distribute the 12 using that distributive property we saw in the review section. And I'll think about what those are later. On the right side, I have 12 times 2. That's 24. So maybe I'll make these red just to remember where that 12 came from. Those 12s were me distributing the 12 onto both terms. And now I'm going to go, all right, I cannot multiply a whole number by a fraction. Let me make that whole number into a fraction. All right, and I think I can reduce here, right? Let's see, 3 can go into 12 4 times. So this just becomes an 8 since it's in the numerator 4 times 2. And the denominator is 1 times 1. So that becomes a lot nicer. How about the next term? I have here a 4 and a 12. They can reduce. 4 goes into 4 once. 4 goes into 12 3 times. So this becomes a 3t. And that seemed like somewhat of a painful process, but I think it was worth it, because now look at the equation that we're left with. This is so much easier to solve. So I think this is a good kind of trick to remember. And then we can finish solving this guy. Let's see, maybe bring it up here. 8 plus 3t is 24. It's just hard to believe that you found the LCD, you multiplied everything by it, and it became so nice. I can't believe it. That's why it's my favorite trick, because it seems like magic. And now, okay, you're trying to solve for t, so I'd move the thing that's being added or subtracted first. Since it's a positive adding, I'm going to subtract it to get rid of it. And at that point, if you want to just say, all right, you know what, 8 and negative 8 cancel. I'm not going to write that 0. That's ridiculous. That's fine. Just write what's left, the 3t. And on the right side, what's left over? 24 subtract 8 is 16. All right, and we only have one step left, and we're having a good time. Divide by 3 on both sides, since it's t times 3. So I'll do the opposite and divide. Then I'll be left with, if you don't have to write the step out, 1t, because 3 divided by 3 is 1. On the right side, though, 3 doesn't go into 16, so I'll just leave it as 16/3. That's a fine answer, no problem with that. So that's 16/3, that's the answer you would have gotten if you solve this problem the old-fashioned way, where you subtracted the 2/3, you would have had to find a common denominator. I mean, just picture that. 2 minus 2/3, get a common denominator, subtract them, and then you'd have to get rid of this 1/4 by multiplying by its reciprocal, and I don't know. And maybe that's not so bad, but there are problems out there that are way worse, and this is a good trick. It'll make your life a lot faster and easier. All right, so if that didn't make perfect sense, it made somewhat sense. That's a good sign. We'll be using that trick a lot more, and I think the more we use it, the more it'll make sense. And we can use actually a similar trick on the next example, because you notice in this first step up here at the very top where it tells you the procedure, it says, okay, if there are many fractions, you do what we just did. But then the next line says, if there are decimals, like we have in example 5 here, I don't like decimals. I actually like fractions better than decimals. So this makes me really sad when I see all these decimals. Especially because I don't want to add them and subtract them and divide them, and it sounds boring. I'd rather bypass all that. And then I think you'll like this trick even better. If you sort of like the trick from example 4, I think you'll really like it from example 5. Let's see, because I guess the thing is, I can take an equation like the one in example 5, and I'm free to multiply both sides of it by whatever I want, as long as I multiply both sides by the same thing. So I'm thinking, all right, decimals. What can you multiply a decimal by to make it a whole number? So as it says up here, if you multiply a decimal number by 10, 100, 1,000, those move the decimal point to the right. You know what I mean? So like if I multiply this number here, 0.76 by 10, that'll move the decimal once to the right, but I don't kind of want to move it twice to the right. So if I multiply 0.76 by 100, 100 times 0.76 is 76. And that's a whole number. I'd much rather deal with that. So looking at all these guys, I noticed if they're all multiplied by 100, then I'm going to get a bunch of whole numbers, and I'd much rather deal with whole numbers. So I think I'm going to do that. I'm going to take 100, and again, 100 because I guess what you need is as many zeros as there are places beyond the decimal in the numbers you're trying to simplify. So notice all the numbers in this equation, the 0.76, the 0.21, the 0.96, and the 0.49, all of them have just 2 digits beyond their decimal. So I just need to multiply by 100. I need as many zeros as there are places beyond the decimal. But if let's say all the numbers only had 1 place beyond the decimal, I'd only need to multiply by 10. But if they all had 3 places beyond the decimal, like if it was 0.765, something like that, then I would need 1,000. You just need as many zeros as you'd like to move the decimal over, or as many zeros as there are places beyond the decimal in your numbers. So it's pretty good. I'm gonna take both sides here, multiply both of them by 100. Uh-oh, kind of running out of room. Hopefully that next problem doesn't mind that I'm borrowing his space. Sorry, little guy. Alright. Good stuff. So 100's being multiplied by both sides. And again, you better make sure that you distribute the 100 onto each term. 100 times 0.76, 100 times 21 or 0.21y, and then 100 times 0.96y, 100 times 0.49. I think that, I mean, on the last example with the fractions, I really wrote it out to really spell it out, but I think I don't really need to do that here. I know 100 times 0.76 moves the decimal twice to the right, making it 76.0, you know, but you don't really need to write 0.0. And then similarly for this 100 times 0.21, if I move that decimal to the right twice, which is what multiplying by 100 does, it'll make it a 21 point, you know, but if the decimal's to the very right of your number, there's no need to write the decimal. It's only if there are digits beyond the decimal. All right, and don't forget your y, of course. That looks a lot nicer. I'd much rather deal with 76 plus 21y. And then on the right side, we'll get something similar. 100 times 0.96, moving the decimal to the right twice would make it 96y. And then similarly for the 0.49, if I move that decimal twice to the right, it'll become 49. And I mean, yeah, these are sort of big numbers, but I'd much rather deal with larger numbers and no decimals than decimals. All right, and this is actually a tricky one too, because this is the first example where we've seen our variable occur twice. So it's kind of tricky. What you want to do here is you want to get your variable terms on the same side. So notice right now we have the equal sign right in the middle. I better be careful. That's like a borderline. Since I want to get both the variables on both on one side, what I want to do is maybe move the 21y to the right side or move the 96y to the left side. I think the way to go is, I mean, it doesn't really matter, both would work, but I think for future more complicated problems, what you're going to want to do is move the variables to the side that has the larger coefficient. That's probably going to make our lives easier in the future. Yeah, let's see. I'm going to move the variables to the side with the larger coefficient. That's a good way to go. So since the coefficient 96 is larger than the coefficient 21, I'm going to want to move the 21 over to the right side. So I guess what I want to do is zero it out. I want to see what can I add or subtract to 21y that'll make it disappear or make it become 0. Well, I'll just do the opposite. Since it's adding, I'm going to subtract it. Negative 21y on the left, negative 21y on the right. I think that'll do it, because you notice here the 21y, subtract 21y is 0. Well, now it's gone, but it's popping up on the right side. On the left side, all that's left there is the 76. On the right side, now I can combine these like terms that are right below each other. It's 96y subtract 21y. That's 75y. Is that right? I think so. Yeah. And then, of course, you have the 49. That's not a like term. All right. And now that we have y only in one place, it's more clear what to do. Now to get y by itself, I need to move the 49 and the 75. But as we saw in example 1, it's better to get rid of what's adding and subtracting first. I'm going to move the 49. Since it's 49 subtracting, I'm going to do the opposite and add it. 49 on both sides. Looking good. Okay. 76 and 49. Let's see. What is that? Is it 295? No, that can't be right. See? All the complicated algebra, and somehow adding is what trips me up. Let's see. Oh, what the heck? I think I'm multiplying in my head. Guys, don't be like me. Don't be silly. That's 7, 8, 9, 10, 11, 12, 125. Hello. I'm losing my mind, you guys. Sorry about that. Alright, so we got 125 equals 75y. Now there's only one thing left to do. Get rid of that 75, huh? I'm going to rewrite it real quick here so we have more room. 125 equals... Uh-oh. 75y. Okay. Looking good. Now I'll divide by 75, and I don't think 75 goes in evenly into 125, but I do think it reduces, right? What can go into 125 and 75? At first I was thinking 5, but I think we can do even better than that. I think 25 goes into both. And I think that'll be it. Let's see. 25 can go into 125 5 times. And goes into 75 3 times. Is that right? Yeah, and 5/3, I mean, come on. Doesn't get much better than that. That's a good looking answer. Yay! We did it! That was a complicated problem, right? Oh my gosh. Holy schmolies. Alright. We're on to the last one. I know you're kind of sad it's the last one. Don't worry, we'll do more in the future. This is very fun stuff, but alas, we gotta move on to bigger and better things. In the next section, we'll see formulas. How do you solve a formula for a certain variable? But alright. In this next problem, I notice, I have a lot of maybe like terms. I'm noticing 19 and 3, they're on the same side of the equation. Sometimes I gotta draw this line so I don't try to cross that. It's like a little border. You can't cross that line. So I see 19 and 3 are like terms on the left. I imagine if this x wasn't trapped in the parentheses, it could probably combine with this x. So I think what I need to do is get rid of these parentheses so that I can combine like terms. But the only way to get rid of parentheses is to distribute. Whatever is to the left of the parentheses needs to be distributed. So I'm going to see, kind of just rewrite the 19. He's just going to be there waiting to see what happens with these parentheses. And here you just have a negative being distributed onto the 2x. It was a positive 2x, but the negative will make it negative. And that 3 was positive, but you're distributing a negative onto it. So it was a positive, now it's going to become a negative 3. Alright, then I'll combine like terms later. Let's see what happens on the right side. I'm going to distribute this 2. Let's see, we got 2 times x, that's 2x. 2 times 3 is 6. And then, of course, don't forget that cute little x that was just hanging out at the end. He's waiting to see what happens. Alright, now I'm going to see if we have some like terms. We have 19 and negative 3 on the left side. Those can combine. 19 and negative 3 makes 16. And then minus 2x, since 2x didn't have anything to combine with on that, on the left side. On the right side, there are a couple like terms here. 2x and x combine to make 3x. That'll be 3x, and then of course the plus 6. 6 didn't have anyone to combine with over there. Alright, now we're kind of down to, I guess, a problem like we had at this point in the last example. Where in the last example we got rid of the decimals, and we were saying, you know what, I see my variable on both sides of the equation. So I think I need to get them together. And as we kind of pointed out in the last one, if you're not sure which side to bring everything on, think about which of these guys has a larger coefficient. So this guy has a negative 2 as his coefficient. This guy has a 3. Well, 3 is larger, so you want to move this guy over to the right, move the x on the left to the right side. Since it's a negative 2x, or you can think of it as it's subtracting, I'm going to do the opposite and add it. And that'll knock it out. It'll disappear from the left side and it'll pop up on the right side. Let's see. So then you have 16 on the left. No more x's on the left because negative 2x and 2x adds up to 0. On the right side, the 3x and the 2x can combine to make 5x. And then don't forget that 6 that's just patiently waiting for something interesting to happen here. Alright, now there's only 1x. So it's all a matter of trying to get him all by himself. So I need to move this 6 over and then move this 5 over. Since the 6 is being added, I'll do the opposite and subtract it. And I think we're getting closer here. Over on the left you have 16 minus 6, that's 10. And on the right side the 6 is cancelled because 6 minus 6 is 0. All that's left is 5x. And then the last step is get rid of that 5. Since it's 5 times x, I'm going to do the opposite and divide by 5. Beautiful. So x is 2. Alright. That's a beautiful thing. Alright, I think that's good. So I don't know if you notice, this one would be a doozy to check. As with the last one, notice the last one had a bunch of decimals and everything. You know what, I think in the last one I'd actually say that doing the problem all over again is probably faster than checking it. That's the sad story. Problem over. is faster than checking it. Because chances are, let's say you did it wrong the first time. If you try it all over again, chances are you're probably not going to get the same answer the second time. You're either going to do it wrong again and get the wrong answer, or a different answer, or do it right the second time, or, you know, and get, anyway. I think this one, though, even though in example 6 we have a pretty complicated equation in the beginning, it was 19 minus 2x plus 3 equals 2 times x plus 3 plus x. It's pretty complicated, but I think because there are no decimals and no fractions, I don't really mind checking that much. But you notice in the last one there were a lot of x's. There was an x here, there was an x here, and there was an x at the very end. So you have to substitute your value in for all of the x's. And then, man, now you can see why we reviewed order of operations, because this is where it comes in handy. So I'm trying to simplify the left side to see what I get. It's 19 minus, I better focus on these parentheses. Within the parentheses I have 2 times 2 and then a plus 3, but we know multiplication comes before addition, so I better multiply first. And then I'll add because I'm still within the parentheses, I'm still trying to simplify that. 4 and 3 is 7. Alright, and then 19 minus 7, that's 12. And now I'm crossing my fingers and praying that I'm going to get a 12 on the right side. That means I did the problem right. So I'm going to go, alright, let's see. Inside the parentheses, I'm going to focus on that. It's 2 plus 3 in there, that makes it 5. And then we have multiplying and we have adding. Multiplying comes first, so I'm going to do that. 2 times 5 is 10, plus that 2. Yay, that's going to make 12. We did it. Yay, you guys. Alright. I'm very excited. I hope it all makes sense, and you know, and I think a lot of times too, maybe it doesn't make perfect sense, it's kind of making sense, but once you start trying your own problems in the homework or whatever it is, it makes a lot more sense. Just, it kind of, math is a very hands-on thing. I don't think I can really just watch someone and really get it and regurgitate all the same steps on the exam unless I really try a bunch of problems on my own. So hopefully it makes sense, yeah, and especially if you try a bunch of problems, I think it'll help a lot. But hopefully everything's been good. We'll see you guys in the next video. I promise we'll mix it up and we'll talk about something new with formulas. And I'll see you there. Thanks for watching.